Hey everyone, and welcome back for another deep dive. Today we are diving deep into a pretty interesting element. One you might not be familiar with. It's promethium.
Prometheum.
Yeah.
Yeah.
Like I said, I don't think a lot of people can be like, oh yeah, promethium,
Yeah.
that's on the tip of my tongue.
Yeah, no, it's definitely not an element you'd just bump into walking down the street.
Right.
Promethium is a synthetic element. It's one of the rare Earth elements, and the thing about it is that it's not naturally found on Earth, at least not in any significant amount.
Okay, so right off the bat, we're talking about something that's not like, we can't just dig it up out of the ground or anything like that.
Exactly, and that makes its discovery story even more interesting.
Oh, I bet. So how did scientists even know to look for this stuff in the first place?
Well, it actually starts back in 1902 with a Czech chemist named Bohuslav Bronner. Now, Bronner was studying those lanthanide elements, that row that's usually kind of tucked away at the bottom of the periodic table.
Yeah, like almost like an afterthought almost.
Yeah, right. But Bronner was really into them, and as he was looking at their properties, he noticed something strange. There was a gap between neodymium and samarium. They just didn't quite fit based on their atomic numbers and other characteristics.
So it's like the periodic table had a missing tooth.
Yeah, exactly. And based on this gap, Bronner predicted that there should be an element there, an element that we now know as promethium.
Wow. So they actually had a spot reserved on the periodic table before they even found it. That's incredible.
It is. But finding it, that was another story altogether.
I bet. So it wasn't just a straight shot from, hey, there's a gap, to, boom, we found it.
Oh, not at all. There were a lot of twists and turns, false starts, misidentifications. In the 1920s alone, there were a couple of claims that scientists had found element 61. They even gave it names like Florentium and Elinium.
So kind of like finding fool's gold. Looks like the real deal, but it's not.
Exactly. And these early attempts just show how tricky it was to pin down promethium.
I can imagine. So what was the problem? Why was it so hard to find?
Well, part of the problem became a little clearer in 1934 when a German physicist named Joseph Matach came up with what we call the isobar rule. Now, without getting too technical, it basically predicted that promethium would be unstable, that it wouldn't have any stable isotopes.
Okay, so I know isotopes are like variations of an element with different numbers and neutrons. But what does it mean for an isotope to be unstable? And why would that make promethium so hard to find?
Well, think of it this way. Imagine you're trying to build a tower, but some of the blocks are wobbly and keep falling apart. That's kind of what happens with unstable isotopes. They're constantly decaying into other elements. So it's like the tower is always in a state of change.
So promethium was constantly transforming before scientists could really get a handle on it.
Exactly. It was like trying to catch a shadow, always one step ahead. But you know what? This instability is actually the key to how they finally discovered it.
Really? That's a twist.
It is. But to understand that part of the story, we're going to have to jump ahead a bit and delve into the world of nuclear physics.
Ooh, sounds intriguing. I'm ready when you are.
So remember how we were talking about promethium's isotopes, those wobbly blocks that are constantly decaying?
Yeah.
Well, you wouldn't believe where scientists finally found it, inside a nuclear reactor.
A nuclear reactor. That doesn't sound like the safest place to be hunting for elements.
You're not wrong, but this was during World War II, and
Yeah.
scientists were working on the Manhattan Project, trying to harness the power of the atom and all that.
Right.
And in 1945, at Oak Ridge National Laboratory, the same lab that produced plutonium, a team there, Marinsky, Glendenin, and Coriell, they were analyzing the byproducts of uranium fission.
Okay, hold on. Uranium fission. Can we break that down a bit?
Sure. So basically, when a uranium atom is hit with neutrons, it can split apart. And that releases a ton of energy. And when it splits, it forms lighter elements.
And one of those elements was promethium.
Bingo. They weren't even looking for it specifically,
Yeah,
but there was hidden amongst all the radioactive leftovers. They were able to isolate it and study it using ion exchange chromatography.
Ion exchange what now?
Yeah, it's a mouthful. But basically, it's a technique for separating elements based on their chemical properties. They were able to pull promethium out from all that other stuff.
That's pretty amazing. So they finally had their promethium. But I'm curious, how did they come up with that name? Promethium. It sounds pretty epic.
It is. And the story behind the name is pretty cool, too. It was actually Grace Mary Coriell, Charles Coriell's wife, one of the scientists who discovered it. She suggested the name Promethium, which was later changed to Prometheum.
I like that, a family affair. But why Prometheum?
Well, it's a reference to Prometheus, the Greek titan, the one who stole fire from the gods and gave it to humanity.
Right. And I guess fire, kind of like nuclear fission, can be a source of great power, but also, dangerous if not handled carefully.
Exactly. The name captures both the wonder and the potential danger of the discovery.
For sure.
Yeah.
So we've got this element named after a titan. It's born in nuclear reactors. We know it's radioactive and unstable. But what does all that mean in terms of its properties?
Right. So as we said, all of Prometheum's isotopes are radioactive, meaning they're always decaying into other elements. And when we talk about radioactive decay, we have to talk about half-life, the time it takes for half of a sample to decay into a different element.
So if we start with, let's say, 100 grams of promethium, after one half-life, we'd have 50 grams left.
Right. And different isotopes have different half-lives. Some are short and some are longer. The most stable isotope of Prometheum-145 has a half-life of about 17.7 years.
Which is still pretty short in, the grand scheme of things.
Yeah.
But here's a question. If all of Prometheum's isotopes are unstable, always decaying, how can we even study it or use it for anything?
Oh, that's a great question. And it gets to the heart of why Prometheum is so interesting. We can still work with it because we understand how it decays and how it will behave.
So it's like knowing a bus route. You may not be able to stop the bus, but you can plan your trip around it.
Yeah, a good analogy. Now, before we move on to what we can actually do with Prometheum, I have one more thing to clear up. We've been saying that Prometheum isn't naturally found on Earth, at least not in any significant amount. Remember that early claim from 1934 by Willard Libby? He thought he'd found Prometheum in neodymium.
Right. Another one of those false starts.
Well, not entirely. It turns out that tiny, tiny amounts of promethium do exist naturally.
Huh.
For example, it can form from the decay of europium-151, but we're talking about such small amounts, parts per quintillion, it's unlikely anyone would have ever found it naturally.
So like finding a needle in a haystack, times a million.
Pretty much. But here's where things get really wild. Remember those spectral lines we talked about? Those unique fingerprints that elements leave in light.
Vaguely. Remind me.
Sure. Each element, when it's heated up, emits light at very specific wavelengths. It's like each element has its own signature tune. And we can use these patterns, these spectral lines, to identify elements, even in stars.
This is like cosmic fingerprinting.
Exactly. And guess what? We've actually detected Prometheum's spectral signature in stars, like in HR 465 in the Andromeda Galaxy.
Wait, so this element that's super rare and unstable here on Earth is just chilling out in stars millions of light years away.
Yeah. And the leading theory is that it's being continuously produced in these stars through nuclear processes.
Wow. That's mind-blowing. So we've got this element that's barely here on Earth, but it's being created in the hearts of stars across the galaxy. So much for being synthetic.
Right. It really makes you think. But that brings us to another question. If promethium is so unstable and so hard to come by, is there anything we can actually use it for?
Yeah, that's what I was thinking. It seems like it would be more trouble than it's worth.
Well, you might be surprised. While not all of promethium's isotopes are useful, there's one in particular that has some pretty cool applications.
Oh, and which Prometheum all-star is that?
Prometheum-147. It's kind of the workhorse of the promethium family. It has a decent half-life, and it doesn't emit those nasty gamma rays. But before we get into that, what are some of your key takeaways so far about promethium?
Well, my brain is definitely doing some gymnastics right now. Promethium, it's like we've gone from a periodic table mystery to this star-powered element with a whole nuclear twist.
It definitely keeps things interesting.
It does. But let's get back to those practical uses for Prometheum-147. What kind of stuff are we talking about here?
Okay, so think about things like those glow-in-the-dark watches, or those signs you see that light up in the dark.
Yeah.
Well, Prometheum-147 plays a big part in making that happen. It all has to do with beta particles.
Beta particles. Okay, can you give me a quick refresher on those?
Sure. So remember when we talked about radioactive decay?
Yeah.
Well, beta decay is one type of decay where a neutron in the atom's nucleus changes into a proton, and when that happens, it spits out an electron. And that's our beta particle.
Gotcha. So Prometheum-147 is shooting out these beta particles. What happens then?
Those beta particles, they can excite phosphors.
Phos?
Yeah. They're special materials that emit light when they're hit by radiation. So those beta particles hit the phosphors and bam, we get that glow-in-the-dark effect. Prometheum-147 is like a tiny, long-lasting power source for those luminous displays.
Okay, so like those exit signs in buildings, could those be powered by promethium?
They could be. In the past, Prometheum-147 was used a lot for signal lights and markers because of that long-lasting glow. But over time, as we've learned more about radiation safety, safer alternatives have become more common, especially in stuff we use every day. You'll still see Prometheum-147 used, though, for some specialized applications like in industrial settings or in the military, places where you need that really reliable, long-lasting light source.
Right, makes sense. Better safe than sorry. Okay, but what about those atomic batteries? Is Prometheum actually powering things?
Oh, yeah, definitely. And this is where it gets really cool. So, Prometheum 147 can be used to create these super long lasting batteries. They're called beta voltaic batteries.
Beta voltaic. Okay.
Yeah. So, basically, you've got a little bit of Prometheum 147 sandwiched between two semiconductor materials.
Semiconductors, those are.
Yeah, they're these materials that can conduct electricity, but only under certain conditions.
Huh.
Like, imagine a gate that can open and close to let electricity through.
Okay, got it.
Now, when Prometheum-147 decays,
Hmm.
sends out those beta particles, those little electron bullets,
Right.
those particles interact with the semiconductors, and that opens up the gate, allowing electricity to flow.
Wow, so the radioactive decay is actually what's powering the battery. That's amazing.
It is. And these batteries are incredibly efficient. They can last for around 5 years.
5 years. That's wild. My phone battery can barely make it through a day. So what kinds of things are these atomic batteries used for?
Well, because they last so long and they're so small,
Okay.
they're really useful for a bunch of different devices. They've been used in things like pacemakers to help regulate heartbeats, guided missiles for navigation, even in some early space probes.
Wow. It's crazy to think that an element that's so rare, and they came from a nuclear reactor, is powering all this important stuff.
Right. It really shows you the power of science and discovery, and who knows what else is possible. Researchers are even looking into using Prometheum-147 for things like portable X-ray sources.
Oh, wow.
Yeah, like imagine a lightweight portable X-ray machine that could be used anywhere, like in disaster zones or remote areas.
Yeah, that would be huge. It's really amazing to think that something so rare can make such a big impact.
It really highlights the importance of understanding the fundamentals of matter,
Mm.
you know. But of course, because we're dealing with something radioactive, we have to think about safety. Prometheum-147 does emit beta radiation, which can be harmful.
Of course. So it's like any powerful tool.
Yeah.
Got to treat it with respect.
Right. That's why anything that uses Prometheum-147 has a bunch of safety features built in. Things like shielding and secure containers to prevent any exposure.
Well, this deep dive has been quite the journey. We started with a missing piece on the periodic table and ended up exploring a star-born element with some truly unique properties and some really interesting applications. It's amazing to think about the journey of Prometheum.
And it really goes to show that even the rarest, most elusive elements can have a huge impact on our lives.
Absolutely. Well, folks, that's Prometheum in a nutshell. Or maybe we should say a nuclear reactor shell.
Yeah.
A big thanks to our expert for joining us on this Promethean adventure.
My pleasure. It was great being here.
And to all of you listening out there, thanks for joining us for another deep dive. Be sure to check back soon for our next exploration into the fascinating world of science.